Modeling the Motion of a Falling Slinky by Logan Betts. The goal of this lab was to build a physics-based model and compare it to real data from a video. I tracked the motion using Tracker and then recreated it with the same situation in GlowScript. The big question that was being aimed to answer is, why does the bottom of the slinky remain still at first? My results ended up showing that the bottom really does stay stationary for a while in both the video and the model. To explain this behavior, we look at three major physics concepts. At first, we have Newton's second law, which states that the motion depends on the net force. We also have drag force, which states that air resistance, which I later included in the model, is a very important factor. And then we also have gravity and spring tension. These oppose each other at the bottom, which turns out to be the key reason it doesn't move right away. Here is the tracker data that I obtained. You can see the bottom barely moves at the start, and then the top collapses downward, and only when the collapse wave reaches the bottom does it finally drop. I used the slinky's mass, its initial position, and 0 initial velocity as my starting conditions for GlowScript. In GlowScript, I modeled the motion by applying the momentum principle. The model updates velocity and position step by step based on the forces acting on the slinky. The simulation has two separate while loops, one for gravity only and one for gravity plus drag. I'll walk through each of them now. The first while loop simulates the slinky with only gravity acting. In each time step, the program calculates the gravitational force, updates the slinky's velocity using Newton's second law, then updates position based on the new velocity. This gives a basic prediction of how the slinky should fall in an ideal environment with no air resistance yet. Before the simulation even starts, GlowScript needs all of the initial conditions. This includes the slinky's mass, its initial position based on my tracker data, its initial velocity, the time step, and the unit vectors. I also set the drag constant here, but since the first loop doesn't use drag, it's basically preparing the system for the second loop. This brings us to the second while loop. The second loop includes both gravity and the drag force. Drag depends on the speed and direction of motion, so this loop updates the force more realistically. The code calculates drag magnitude, gets the direction using the norm function, and then applies Newton's second law again to update velocity and position. This loop makes the simulation better match what actually happens in the real world, considering the drag force. The results. When I compare my predicted model to the observed data, they matched very closely. They both show that the bottom staying basically stationary at first, and then both show it dropping once the collapse wave reaches it. Any small difference comes from the real-world factors we didn't perfectly model. This could be any tiny external forces or human error when clicking tracker points, so anything that comes from tracking it in Tracker, basically. So, for the discussion, why does the bottom remain still? Right when the slinky is released, the upward tension from the stretched coils exactly balances the downward force of gravity. Those forces cancel out, so the bottom does not accelerate. Only when the collapsing coils reach the bottom does the tension suddenly disappear and the bottom finally falls. For the what-if question, we asked what happens if we attach a heavy weight to the bottom. The answer is that it depends. If the slinky's long enough or stiff enough so the tension can still equal the weight force, then yes, the bottom will stay suspended. If the weight is too heavy, then the tension can't balance gravity and the bottom will start moving immediately. In conclusion, combining Tracker with GlowScript let me build a very realistic model of the slinky's motion. The physics lines up very nicely with what we see in the video, and the model helps explain the really weird phenomenon of the bottom staying still.